All right, set 25. We have problems 37, 39, 40, 25, 27, 28. That sounds like a lot. Let's hope that these are quicker questions than the last few were, or we'll be here for hours. All right. 37 says, two cars are stuck in a traffic jam and each sounds its horn at a frequency of 625 hertz. Bicyclist between the two cars, 4.5 meters from each horn, is disturbed to find she is at a point of constructive interference. How far backward must she move to reach the nearest point of destructive interference? Now she's disturbed to find that because she is, when the two peaks come together, it's going to be much louder in her ears, whereas if it was not two peaks coming together, it would be much quieter in her ears. So I am not going to attempt to draw this because my attempting to draw cars is ridiculous. So let's just make little lines here and little bicycle here. So this is 4.5 and this is 4.5 and this is the bike. Okay. So what are we looking for? We are looking for delta x. How far must she move back? All right. And what do we know? We have F equals 625. And we know that our, let's call this D equals 4.50 meters. All right, so what equations do we know? So we know that constructive interference, we have R2 minus R1 equals N lambda, where N is an integer, 1, 2, 3, ... Destructive, we have R2 minus R1 equals N plus 1/2. Again, N is an integer, 1, 2, whatever. We know B equals lambda F. That's all I had written down for your homework. I think that's all we need to solve this. So destructive, R2 minus R1 equals N plus 1/2. We can say this is 0 because how far back does she have to move? It doesn't say how far back can she move. It's how far back does she have to move. So it's really the first destructive wave here that we're looking at. So R2 minus R1, our R2 is going to be our 4.5 plus delta X. Because remember, we're going to have this. So we're going to have this. We're going to have plus a delta X, right? So this is going to be our new R2. And then this is going to be our new R1. And so our new R1 is going to be our original R1 minus delta X. All right, so both of our R1 and R2 are 4.5. So we can write, excuse me, 4.5 minus delta X minus 4.5 plus delta X equals 1/2 lambda. Let's rewrite this for lambda right away. So we've got lambda equals V over F, and we know that V, we know, you can just look it up online. I think your textbook somewhere tells you, but so sound waves change moving through air as the temperature of air changes, but if they don't give you a temperature, you can just take the velocity of waves in air to be 343 meters per second. Now, if they give you a temperature, use that temperature and use the equation that your book gives you to find out what the velocity will be. All of the problems I believe that we're doing for this, you don't need to figure out temperature dependence. You're just using the 343. All right, so plugging that in, we get 343 over 625. Okay, so these cancel out because we have 4.5 minus 4.5. These don't cancel out because we have negative minus negative. So we have -2 delta x equals, and now we expect it to be a negative because it's how far back does she have to move, not how far forward does she have to go. So we're solving for delta x equals over 4 equals 343. And if you punch out into your calculator, you get something that looks like 0.1372, or delta x equals 0.137 meters. So that is our answer for that one. Oh, there's no A and B. Okay, maybe we will not be here all day. All right. 39 states, the ship in figure below travels along a straight line parallel to the shore and at a distance d. The ship's radio receives simultaneously signals of the same frequency from antennas A and B, separated by a distance of L. The signals interfere constructively at point C, which is equidistant from A and B. The signal goes through the first minima at D, which is directly outward from the shore from point B, determine the wavelength of the radio waves. That is a mouthful, and I actually did this problem wrong the first time that I did it because I did not read the problem clearly, even though they gave a little diagram here. I did not do it properly. Okay, so we've got, let's see, point A, point B, point D, and C is in between here. All right, so all right, so this is L. This we're calling D. We know so right away we're looking at triangles. So when I redid this problem, I just went ahead and solved for the triangles right away. I ended up only using one of them, but it doesn't hurt to solve for both of them, right? So this is A, B, C, D. So I solved for this triangle. Okay. So it's really A, B, 2. And then this is AC. And this is D. I ended up not needing that one, but it doesn't hurt to solve for the triangles that you think you might use. The one that you do end up using is this one here. So you've got A, B, D, this is L, this is D, this is AD, and we know that, and I know that we know that. I don't have to say this is how we know it because we've used this many, many times in the book. Professor gave it to us our first week. We know for sure AD equals square root of L squared plus D squared equals square root of 800 squared plus 600 squared gives us 1,000. And that is meters. Oh, we should have wrote down what we know. Whoops. 600. It was 800, obviously, because we've used them over here. All right, so we're gonna use the same equation we did last time. Again, we can set n to 0 because our problem doesn't say the third, or it says our first minimum. So this again, we can say 0. So we've got r squared, or r2 minus r1 equals 1/2. Lambda, we're solving for lambda. So we have 2 lambda equals 2 r2 minus r1. And now we got to look at what's R2 and what's R1. So our R2 is going to be this. Our AD is our R2 because our boat is at D. And our R1 is D because the problem says the ship's radio receives from antennas A and B. So B here, A, D. So from A to B and from A to D, R2 to R1. Okay. So now we're just punching in, putting in values, and we have 2, 1,000 minus 600 equals 800. So we have lambda equals 800 meters. And again, there's no A and B. Okay. Moving along. 2 loudspeakers are placed above and below each other as in the figure. So let's draw the figure. This is red. This is red. Red, red. Let's call this L. Let's call this D. Okay. They call this R2. They call this R1. And then we have little speakers here. Ooh. Okay. So our question says, so right here. Two loudspeakers are placed above and below each other as in the figure and are driven by the same source, a frequency of, given it an observer, O. At the same distance from each speaker, what minimum vertical distance upward should the top speaker be moved to create destructive interference at O? All right, so we're looking for, delta X here. So what do we know? We know, well, we're looking for delta X. We know F equals 4.50 times 10 squared hertz. We know R2 equals R1. We know that's it. That's all she wrote. Oh, we know D equals 8.00. No. D equals 3.00. L equals 8.00. So looking at our little triangles, this is R1 equals R2. We've got 1.5. We've got 8. So we have R1, R2 equals square root of 1.5 squared plus 8 squared. We know, again, R2 minus R1 equals 1/2 n plus 1/2. It's, again, we can just do our first. So this is 0. We know V equals this. So C over F equals 343 over 50. All right, so we have R2 minus R1, but this is not what our triangle shows. That is going to be our R2 is going to be this line, which in my homework I called R1N. So our R2 is R1N minus R1 equals 1/2 black. And R1N, the purple line that I have here, the arrow, is going to be R1N equals D plus delta X L. So R1N equals square root of D plus delta X squared plus L squared. So we're going to have square root of 1.5 squared plus delta X squared plus 8 squared minus R1 equals 1/2 here. And we know that R1 got 1.5 plus delta X squared plus 8 squared minus 1.5 squared plus 8 squared equals that. If we square, rearrange, we end up with 1.5 plus delta X squared plus 8 squared equals now if we do the math on all of this, we get Oh, sorry, I said that wrong. So we're going to square this because we're going to use our quadratic formula. In order to do that, we got to figure out what x is. So we're going to square that. And we get delta x squared, which is going to be our x, plus 3 delta x, which is going to be, this is going to be our a, this is going to be our b, plus we're going to have 2.25 plus 8 squared minus this. This is going to be our C. So let's use our quadratic. X, delta x equals negative b, negative 3, plus or minus the square root of b squared. So 9 minus 4 times 1 times, if you do all of that, we end up with 66.25. That's what this is, minus 72.597, blah, 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 blah. And that is all over 2 times 1. We do the math on this, we end up with 5.86. So we're going to end up with negative 3 plus 5.86 all over 2. That gives us 1.43213, or delta x equals 1.43 meters. Now, quadratic says plus or minus. It says that we're going to move up. So we're going to want the positive. The negative would be how far we would have to move down, and we don't care to know that. So we went with what's going to give us the positive answer, and that gave us the delta x equals 1.43 meters. Again, this one doesn't have A, B, C, or whatever. All right, 25. 25. Baseball hits a car, ouch, breaking its window and triggers an alarm, which sounds at a frequency of 1250. So we got baseball coming in, breaks the window, and then we've got a bike. Use this for V. It's heard by a boy on a bicycle riding away at 6.5. So 6.5 meters per second. What frequency is heard by the boy? Okay, so we are looking for F. We know the velocity of the bicycle. That is 6.50 meters per second. We are given the frequency at the window, and that is 1250 hertz. All right, so we got figuring out sound when something's moving away or getting closer. So obviously this is the Doppler effect. So what do we know about the Doppler effect? So here are the equations that we know. O is observer. So frequency of the observer equals Fs, V plus V naught over V minus Vs. All right, so we will change this to make sense for our problem, and we will say V of the bicycle, because our observer is on the bicycle, VF at the window. We have V plus V naught. Oh, sorry, V minus V naught, because he's moving away. And the window isn't moving. So BS is 0. And then we just plug in what we know. So we have the frequency at the window, and that's 1250. 343 is the velocity of sound through air. Again, we don't have temperature, so we're assuming that it's not temperature dependent. V naught is 6.5. And again, we have 343. So this is just plugging into a calculator, and then we end up with 1226.3195. We want 3 significant digits. So we have the frequency heard at the bicycle is 1230 hertz. That one again is just find the right equation and plug in numbers. All right, 27. 27, a commuter train passes a passenger platform at a constant speed of 40. The train horn is sounded at its characteristic frequency of 320. What overall change of frequency is detected by a person on the platform as the train moves from approaching to receding? So we've got a person standing here, and we've got a train coming in and a train moving by. So we are looking for we're looking for what our delta F is. We are given so this is V equals 40 meters per second. All right, so we were given F of the train, so we'll call that FT. We were at 320 hertz is what we were given. We have velocity of the train. That's going to be 40.0 meters per second. All right, so we are looking for delta F. And so delta F is going to be, it's going to be what the observer hears as the train, before the train reaches him. So we could say the observer before it reaches him minus the frequency heard by the observer after it passes him. So our observer isn't moving, so we know that V naught is going to be 0. So we have FT, so the frequency of the train, times V minus V naught. So before it reaches the person, it's going to be V minus Vs. And F after he passes is going to be F, the frequency of the train, V minus V naught, V plus Vs. So delta F equals FT V. Our person on the platform stop moving. V minus Vs minus FT V plus Vs. Now we have all these values. It's just a matter of plugging in what we have. So delta F is going to be 320. That is the frequency of the train, which we were given. We've got 343, which is the velocity of sound. 343 minus 40, which is the velocity of the train, minus 343 over 343 plus 40. And plug it into your calculator, we end up with 75.664, or delta F equals 75.7. If we look at these two numbers, we can see that this number is smaller because the denominator is larger. So the frequency will drop. So this will be smaller. Okay, so B says, what wavelength is detected by a person on the platform as the train approaches? All right, so what do we know? We know this. Oh, not after, before. All right, so we know that. We can rearrange for this. We're going to use 343, and we're going to use, before, we're going to use what we found here and plug that in here. And that is 343 over 343 over 343 minus 40. And you end up with 0.9468, or our wavelength is 0.947 meters. And there you go. All right, 28. 28 says, an airplane traveling at half the speed of sound emits a sound of frequency 5 kilohertz. At what frequency does a stationary listener hear the sound as the train approaches, as it passes? So we got a plane moving at 343 over 2. And we are looking for A is going to be FOB. We know that's going to be F. Let's say plane. V over V plus VS equals 5 kilohertz times 343 all over 343 plus 343 over 2. And we end up with 10,000 or 10.0 kilohertz. And B says, as it passes. So now we're looking for FOA. And we know that FOA is going to be FP, which is the frequency of the plane. V over V. Did I write this wrong? Oh, I'm sorry. I did. I skipped ahead to V. Yeah, this is V minus because it's approaching. My bad. Sorry. This is V plus VS. And we're going to have 343 all over 343 minus 343. I hope you see that a lot of the stuff can cancel out. We end up with 3.3. Forgot the 343 over 343 plus 343 over 2. Again, lots of stuff cancels just like it does up here. We end up with 3.3 FOA equals 3.33 kilohertz. All right. So that does it for our week 7. I will see you next week, our finals week, where I will give you the answers to not a homework assignment. So there is no homework assignment, no quiz, as I said before. But you do have discussion problems. I will post discussion problems, solutions, and video. Good luck on the final.